So this is going to be the session on the unified approach to model and code verification. Just first want to introduce myself. My name is Chuck Alaski. I've been at MathWorks about 3 years. Before that, I was at GM for about a dozen years or more, really focusing on model-based design and testing within that process. So I'd like to introduce Anthony.
Thanks, Chuck. Hello. Is the mic? Now you guys hear me?
Yeah,
okay.
You're on.
Perfect. My name is Anthony Abraham. Before I joined MathWorks, I was an embedded software engineer for aerospace industry called United Technology. So I've been at MathWorks close to a year now.
Okay. All right, so go ahead and get started. So just kind of talk a little bit about motivation. So most of our customers have a combination of model-based and hand code, right? We try. When I was at GM Fuel Cell, we had a lot of model-based design, but we still had some diagnostic and some other infrastructure that was hand code. So we're basically trying to answer some of those questions where you might just hear completely a model-based kind of a process, or you might just be code-based, and that's why we've kind of put this together to how do we efficiently test hand code and as well as our models. So within here, you might notice that we do have tools for testing models as well as testing code. And in the past, we've been asked questions at events like this, and maybe not done the greatest answer on this, like how do I use Polyspace in this environment? And that's really what we're going to try to go through and show how we can have these tools work together. And in the end, we'll put together and show a workflow where you have some model-based verification and code-based verification, and when you can do that. So kind of going in, you might think all of the code verification happens in the end, but that's really not what we're going to show. We're going to show how you can do code-based verification earlier in this, and again, have it all work together. Okay, so just run through this quickly. So what we're going to be talking about is static analysis before functional testing, and that's static analysis of the model and the code. And then not really the focus of this, but just for continuity, we'll show a little bit of dynamic functional testing and some of the results from that. And the key thing here is we're going to be looking at testing of the model S function and the generated code. And then last, we'll look at a static analysis of the integrated code. So that's generally probably where a lot of you are, where you do your model base, and then your integrator puts it all together, and then maybe you put it on the hill bench. And then again, we're going to show a unified complementary workflow of how these work together. Okay, and then the idea here is also, with each step, you increase confidence in your design. So we're going to show a cruise control application with that, and it operates exactly like what most of you have in your car. It sets the target speed, as well as we have something to set the pedal position as well based on your inputs in the car. And so, like simple case, say we're going to 65 miles an hour. You set it, and you basically power it on. You set it, and then it drives it to 65 miles an hour. And to show kind of like again the model in code verification, we're going to have a C code application that's going to have some hand code components in it. We also have a model-based stateflow component in there. And then last, we'll also kind of show a hybrid where we bring in some C code into the model, so we'll have an S function component with that. Okay? All right. So we'll take a quick look at the architecture. So in the center, we have our cruise control application. We have a set of inputs. As you might expect, we have power on, brake and vehicle speed, as well as a decrease or set button, or an increase or resume button, just again like what you have in your vehicle. And then for outputs, we're going to have target speed, engaged, and pedal position. So inside, we have some hand code, so our function scheduler will be hand code. And then we'll have some hand code to read the inputs. And also we'll check some of those inputs and do some fault logging with that. Yep. And we'll then have a completely model-based generated code component, which will be our target speed control module. Okay. And then this will be, again, kind of our hybrid model with S function code in it. And then last, we'd be writing the outputs. Okay. So to show this, I'm gonna take a role, Anthony's gonna take a role to kind of go back and forth and kind of engage in a conversation on this. So I'm gonna be the model-based design controls guy. So I really do everything in Simulink, develop all my models. So I'm gonna be doing the target speed control module. And again, we'll have this pedal command control module where I'll bring in an S function. And then I generate code and then deliver that to Anthony. And my testing is I rely on the model-based testing for that. So now I can turn it over to Anthony.
Okay, thanks, Chuck. Yes, my role in this will be I am the integrated and the build guy, where I develop C code to read and write IOs, and for fault logging purpose also to log the fault into non-volatile memory. I also integrate the hand code with the auto-generated code that Chuck delivered to me. Yep. I also create the final ECU build for the cruise control application. And finally, I rely on my test on the Hill bench. Okay. Okay.
So,
I
can do this. Okay. So we're a software supply company. We're going to deliver our first production release to our customer. So we've been doing a lot of prototyping work on our own development ECU. So now we are going to have to do add some features and a few changes. And by going through this, we'll kind of show some of the methods that we're going to use. So one thing is, I was using, again, a prototyping controller, so I had a lot of things just in floats, and now I'm going to move to integers for my signals and cals for the target speed module. The customer has actually provided us with a lookup table to facilitate their calibration, so we haven't had that, so we need to bring that into our pedal command module. And then they're also saying for the generated code that we need to demonstrate that that's Misra compliant. So we're going to, again, show how we do that. And then within some of the hand code, right, we're going to remove some unused fault code. Maybe you want to talk about this.
That's correct. The hand code modification are very minor, which is removing unused fault record, and also making a minor changes to the new ECU to read a 12-bit instead of a 14-bit A2D data. In addition, the customer also requires us to provide a functional testing on the integrated product. Okay. I'll hand it over for
Okay.
model.
So we'll first talk from the model, so the model-based design tasks. And the idea here is that what we're trying to do is test early, within the mantra of model-based design. And so by doing that, we're going to look at what checks are available to us to, again, facilitate this testing early. So we're going to, again, look at the task of converting the signal cals to floats, or to integers, excuse me, and include the customer table, and then demonstrate the code is Misra compliant. So again, the approach here is to do these checks before functional testing, early in the development to minimize rework, because we've done this in the past, right, and we've tried to do the Misra checking very late, and we end up, possibly missing our deadline. So we want to try to make this, do as many checks as we can early on in this environment. Okay, so first look at this. And one thing we can do in our model is we can actually check for design errors. And so this is using DesignVerifier, where it's going to check check that we don't have, in this case, dead logic. So we can configure this to say, let's just look for dead logic based on now that we've gone from floats to integers, okay? And then when we do this, it basically goes through, on the ranges and so on, and it looks to see if there's any logic in there that can say only be true, only be false, but not true and false. So if it's dead, it can only be true or false, but not both. And so when we go through, it identifies about 70 objectives, and then we can again use the model, coloring on the model to highlight the areas where we have some dead logic. And again, this dead logic would really hurt us with our functional testing. So if we didn't know this ahead of time, we could be spending a lot of time to try to improve our coverage in this case. So when we take a closer look at what the real issue is, it turns out it's this transition that can never be false. And one thing we can do in the model is you can insert a breakpoint on that transition, and then within the command window, we can go through and look to see what's going on. So we can basically diagnose that after condition and see why it's saying it can never be false. And what happens is that we look at the ink deck, which is 1, the hold rate's 5. So we have a division of 1 divided by 5. These are both UN8s, and what happens is we basically have integer math. So rather than have this, again, maybe be uncovered in functional testing, we're showing this early on by using designer detection to again, define this early. And then we can play around with the order of operation, and we can see, yes, in fact, that's always 0, so that after condition would always be true. But if we rearrange it, we find out that we can fix it by just changing the order. So again, that can save us some time for the functional testing. Okay, so we've done that. And now we're going to look at including this lookup table to support calibration. And I think you've done some work in this area, right, that can help us in this area.
Yes, Chuck. Before we start simulating and testing the model, we could be able to look at a single block if we have a runtime error. In this case, we're going to analyze an S function, this is a Simulink block containing an S function, where I could be able to run a bug finder, a Polyspace bug finder, by going through the model. So, Chuck, when I tried to analyze this thing, I found an error. In this case, the window that we're seeing on the right side is a bug finder error. At the bracket, as you see, is there is some defect. That's what the red is.
So you were able to launch this right from the model?
That's correct.
Okay. So it's something maybe I could do later on. Once
yep.
You give me some idea of how it works.
Exactly. That's correct. Now, if I click on the right bracket, it's saying that there is an array access out of bound, which means bug finder knows the range of the arrays from 0 to 10, but we are trying to access the 11 element of the array. So we all are engineers. We can't just fix things and move on. We always like to know the root cause of the problem. In this case, I'm going to talk about what's really the issue here. Okay. This contains the global declaration of the speed delx, which contain 11 elements, will be the correct range will be 0 to 10, which this speed delx is passed to a parameter called lookup table function. If we look at closely and pay attention, there is a my size, which is hard-coded to 11. And down below, we have kind of, I call it, a more defensive mechanism of coding, which is preventing not to have a non-terminating while loop. So that's why we are checking index is less than my size. However, by the last element of that index, it's going to be 11, and when we try to access the 11 element, that's why we have array bound out of access issue. Okay. To fix this,
so we're only off by 1?
Yeah. Well, it's yes, you're absolutely right. It's off by 1, but And to fix this, it's as simple, we're going to keep our defensive mechanism, but we're going to subtract by 1. And we're going to rerun a bug finder from the model again.
So, but like in that case, if we access 1 extra, we don't know really what would happen, right? You could have some really unexpected results.
Exactly. If we download the system into a real unit, we don't know what kind of data that we are reading. So, okay. So we can rerun it, bug finder, and bug finder will tell us, okay, there is no defect on that S function. Okay.
Okay. So that looks like it could increase our confidence now in that S function that we got from the customer.
That's correct. So before we proceed, we could be able to see that a single block does not contain any runtime error. Okay. So we complete that task. And the next one is we also have to comply with Misra. And so for Misra, from the model aspect of it, luckily I'm surrounded by a lot of good application engineer at MathWorks, so we could use actually a model advisory to.
So again, we're trying to check this early, right? We're not waiting till we generate the code and integrate it.
So this is just a preliminary check that will allow us to do our configuration is correct. So for this example, I'm going to select all of the Misra guidance for C 2012, which contain the auto-generated code configuration setup is correct. And also, we don't have a non-recommended block inside our model. Okay. This will be, we're going to run the selected check, and this will give us the result, which is saying that the majority of the result is correct. However, we have one defect to address. That defect is saying that if there is a model verification inside the model, that needs to be disabled. And this is as simple as clicking modify all, which will change the current setting into the recommended setting.
So this helps us to say, at least with regard to the model, we have the right settings and the right architecture, using the right blocks for at least trying to get us to be Misra compliant.
That's correct. It's just
so, and we're only showing like on the target speed. We could also we ran this on the other module as well, right?
Yeah,
we
we
run
could
on both.
Yeah. Okay. So we're gonna rerun the check again and see that all of the checks is passed. Okay.
But you just used the modify button and it just automatically changed it.
That's correct.
Yeah. Okay. So that's good.
So by saying this, what we are saying is we're not claiming that the auto-generated code will comply with Misra. The auto-generated code will likely comply with Misra. We are just minimizing the defects. Okay.
So how do we ensure with Polyspace then, or?
Now, how do I guarantee the entire source code comply with Misra? How many violations that I have? In this case, we could launch Polyspace from the model.
Oh, okay.
To pretty much configure Polyspace. In this case, we're going to open the Polyspace option feature, where it will allow us to configure Polyspace. Okay. In this, as you can see, that there is an option which is there are pre-selected OBL stand for obligatory rule, but however, if you care about only the couple of checks, you could select the down button where custom, where you could be able to check the one that you
But for the customer, we just had to do the obligatory ones?
For this, yes, we decide to do just the obligatory. Okay. And we're going to save the Polyspace configuration, and we're going to go back to the model again. We could run the verification. So again, we're not leaving the model. We are just accessing the Polyspace feature from the model. And when we run it, here is the result that I have. There are a total of 18 violations. And the violation that I'm going to concentrate for this demonstration is only 14 of them. So this violation is talking about this, the data file. The global declaration should be located in its own data file. So how do we address this from the model? As we all know, we cannot change the auto-generated code. So from the model, there is a code placement option where I could actually select under the code configuration that allows me to put all the global variable into a data source file.
Okay.
Okay. And we rerun Polyspace again, and as you can see, it lowered the defect from by 11 violation. So I don't know anybody experience, but in my experience, it's almost very difficult to fulfill Misra violation. Some of the violation, it could be addressed by adding a justification for it.
So we have a little code generation kind of artifact in there that we have to put some annotation to recognize that we actually found it and acknowledged it.
That's correct.
Yeah.
So
Okay.
we can fix that. So
Okay.
right.
Maybe next release. Okay.
Yeah. So we demonstrated the generated code is Misra Compliance, and as Chuck always say, what we're doing here is step by step we are trying as much as that we can. By the time we get to the code generation, we'll have less violation to address.
Yep.
Okay, I'll
Sounds
hand
good.
it back to them.
Okay. Okay, so we did as much as we can, really, before our functional testing, again, to try to minimize our rework. So we need to provide test results. Customers asking for that for the model-based modules. So again, I'll run through this somewhat quickly, again, because I don't think this is really so much the focus, but just for continuity. But we can do functional testing of the S function. That's in our pedal command module, and we'll also show a quick equivalence testing. Okay. All right. So again, this is our pedal command. The center block there is our S function. We can bring this into Simulink test and create a harness, and then we're using basically in the center is our unit under test, and then on the right-hand side we have an assessment. We're using, again, the test sequence block with that, and that allows us to really, that test sequence block, we can make it so it's an oracle, meaning it can generate expected results as well. And then on the left we have signal builder, and these test cases are actually generated as well. So we go ahead and run those, and we do, in fact, we do pass it, but we do have, again, due to the model coloring, you can see we have some coverage, not 100% coverage in our S function, okay? And so one thing we have now is we can do code coverage. So most of you guys are probably familiar with model coverage, but we can also do code coverage analysis within our S function. And again, this looks somewhat familiar, right? This is our kind of our defensive programming, and it's really saying that the second condition is always true. And really that's because we kind of put the defensive programming in there, and it has to do with because this looks at the actual parameters and parameter values, and with those
I see.
values, it's not possible for that to, because the previous if and else checks were filtering that out.
I see.
So, but we're able to understand why it's not 100% covered, but again, we can see that we did a pretty good job for testing this algorithm. And then next we will run through an equivalence checking. Again, here we're going to look at model to code, because you might say we're doing all these tests in the model.
Yep.
Is that real? Maybe we need to check the code as well, right?
I'm curious about how do you guarantee that you're testing the code?
So in this case, you know, we have a harness again. This is the same harness that we used for doing the model-based tests.
Okay.
And then again, we can put that model reference. We can put the model that of our target speed control. We can put that into a SIL mode. So if we do it in SIL mode, it'll generate the code similar to the code that I deliver to you.
Okay.
So again, I can test the code early on this way. Okay. And I can then bring this again into Simulink test, and then those are my results. So I have like over 19 test cases, and so those are passing. And again, all it's really doing, it's just taking your model and then comparing it to your to the SIL equivalent of that. So the baseline is the model, and then we're comparing that the SIL results to that. So you feel confident that we're in pretty good shape?
It's pretty nice where we could be able to simulate.
And then the other thing we can look a little more closely is we can look at our coverage.
Oh, I see.
So that's another piece that we get out of this. And so we had high coverage, 100% coverage vectors in the model. And then in this case, we actually have a little slight differences in the coverage on the code, because there's a few additional artifacts that are created there as well.
Okay.
But this points us to that area. And we also have a coverage report of the generated code, so we can look exactly at where those differences are.
Okay.
So, okay.
Cool. That's pretty cool.
All right, so keep going on here. And so now we'll get to the integrated code. So I've basically generated the code, and I've given it to you to check out and run on your Hill bench, because that's the way you like to do your testing.
That's where the fun begins. So my task is to remove unused fault record, and which is already done, and migrate the code, which is reading the 12-bit A2D instead of the 14-bit A2D data. And Chuck, I'll be honest, those are just a minor change that I have made. So that's already completed.
So you feel pretty confident that it's going to work?
I feel confident that it should.
Okay.
It should work. And the final ECU build is made, which contain the hand code, the S function, and the auto-generated code. Okay. Now we need to take it to the Hill bench, where we are trying to find an issue during integration at the Hill bench. Okay. Okay. Well, unfortunately, Chuck, I found two issues at the Hill bench.
Oh, okay.
The first issue is the cruise control power itself off while I am doing a fault injection test. The second issue is the target speed. It's just never exceed 40 miles an hour.
Huh. So why do you think it's powering off?
I don't know. I mean, I could visually or manually inspect it if there is anything that I could find.
I mean, some of that, it's in the model-based code. You think it's in my stuff that possibly?
It is really very difficult to tell.
I don't think I'm controlling the power, though. I think that's coming from you, so.
Yeah.
Okay.
So.
In the same way with the target speed, I checked, where it could go up to like 90, so.
Okay. So what, maybe perhaps we could try to use a tool?
Yeah, I found some pretty good stuff, right? We're looking at the model-generated code. Maybe Polyspace can look at your integrated code and help us out.
So let's use the Polyspace in this example. this is the Polyspace code prover project, which contain analog inputs that read and write IOs, the scheduler, and the fault logging. It also included auto-generated code. Okay. It also includes our S function that's delivered from the customers. Okay. The code prover result is showing me that there is actually a non-terminating loop in a hand code at the fault logging.
Could be nasty.
Yep. So this is a call hierarchy from the code prover, where it's telling me there is a non-terminating loop at the a non-terminating loop in the fault logging function. Okay. If I go to
so what does that
fault,
mean? What does non-terminating loop mean?
A very good question. I'll describe it as I go.
Okay, I don't understand the term, but
so a non-terminating loop is caused by a pointer dereference, and that pointer dereference is causing a non-terminating loop. Okay. In the next slide, try to describe a little bit better. Okay. So let's briefly look at this fault log logic. It is a very straightforward file. All it does is it copies the current fault log and it stores it into a circular buffer, where it eventually stores into a non-volatile memory. And after that, it clear it back to 0. So Chuck, if I visually inspect this, and I know the memory location of where the fault record reside, and if I put just walk it through, as you can see, index 0 to 10, everything is valid. Okay. However, when I step into the 11 index, it's actually overwriting the next memory location.
Okay. So it looks like your stuff is writing over that.
Yes, you could
shut my cruise control off, right?
Yeah. Okay. So in this case, the hand code was causing the cruise control on and off switch to turn off. Okay. I can't just gradually fix it and move on. I like to know what I have made a mistake for.
Sure.
So in this, I removed those 2 fault record elements, okay, which was 12. Now it's to 10, okay?
Looks like a small change.
It is a minor change, but the thing that I overlooked is I forgot to change that index value from 12 to 10. Okay. Well, I could say fix it, or I could just use the tool to make sure again.
Yeah, I would.
Yeah. So, I rerun the tool again, and I rerun the code prover again, and verify that the function is there is no runtime error on it.
Great.
Okay.
So,
right.
can we show the
sorry.
So we have the.
And now, if visually we, look at it, it will go through, and it's not gonna overwrite the cruise on and off a switch.
Nice. That's good.
Okay. So that is a definite fix. So
yeah, something we probably should run before hill testing.
Absolutely. So, but however, the second one is very interesting though. So it is actually finding dead code on the generated code. So and let's look at the code stack again. The code stack is saying that there is actually unreachable code on the auto-generated line. On the auto-generated module.
I understand that term, unreachable.
Okay.
That's good.
That's good. It takes a little while, but
it takes a while. I'll get up to speed.
Yeah. I feel the same way about models, so it's okay. All right. So let's look at what's this unreachable code mean. Okay. And in this case, code prover, it knows the range of the speed is going to be from 0 to 40. And the max T speed is a constant. It's set for 90. So it will never reach that chunk of a code.
Okay. But in my model, I think I was able to get up to 160, but
yep.
Okay.
That's right. And so the changes, again, it's really, 14-bit to 12-bit.
Right.
Okay.
Another minor change, though. Right.
Yes, they all are minor changes, but as we all know, minor changes usually have a major defect. But all right. So the speed max, which is set to read only 12-bit, which will be used in this read input.
Okay.
This read inputs is used a mask, which is good. However, the conversion factor is also has to be defined to change the the sensor data into a mile per hour.
So
where
that needed to be like increased
exactly
by 4, right?
It
Because
should-
we went
should
down
be.
2 bits.
exactly.
We
It
had
should be
4 times less counts. And,
yeah. So
okay.
it should
So that's
be,
why maybe instead of 160, we went to 40.
Yep, exactly. So that is the cause of the issue, and so that's what I have.
Okay.
Chuck, I will hand it back to you. Yep.
Sure. Okay, so now we just kind of want to summarize, what we've gone through here. So at the bottom, we have our MBD generated code workflow. And then at the top, we have just a small snippet of the hand code workflow. And then we have our integrated code, let's say, that we actually created the cruise control application.
Yep.
And so now when we look at some of the checks we did, so in the center there, that's the model that we actually use for production code generation. And in our case, we did these checks before functional testing, and we checked early for these design errors, again, to minimize rework in the functional testing, or maybe even all the way if it got to the integrated. Because perhaps some of these checks may not have been caught even with some of our functional tests. And then we also, because we got that S function that we were concerned about, we're from the customer, you're able to help me with that so we can check that early, again, before we even did the functional testing. And then the Misra part, key thing here is we did some stuff with Model Advisor. We checked as much as we could in the model to kind of ensure that we'd have minimal rework. Again, not a complete guarantee. So it's kind of a handshaking between the Model Advisor checks and what we did with Polyspace for the final checks.
That's correct. That will kind of guarantee that the Misra violation.
And again, we did that before functional, so we knew we had, when the code I delivered to you was going to be Misra compliant.
That's correct.
So then after that, I then did the functional testing on that. We did show where we could do code coverage in the S function, so you get an idea how well that was tested, and then also the generated code where you had more confidence that it was going to behave on your hill bench the way you'd expect.
That was actually pretty cool, where you could be able to test the code without having a hardware. So
Yeah, virtually, right?
yep.
So the other one is with our, one of the things we have in order to facilitate that equivalence testing of the model code behavior, we had the integrated SIL mode support, which was basically just a click. It was very simple to do. Just do a mouse click and it generated the code, and I was able to reuse the same test harness, and so it was very streamlined, very efficient. And then we could look at the code coverage in SIL mode as well. So we had really good confidence that what I delivered to you is pretty much ready to go.
Yep. So that's why all of the defect happened to be on the simple change that I have on the hand.
Right. So in that case, that's where we did, after we found those issues, we said, hey, let's go back and look at that integrated code and see if Polyspace can help us out. And it found, the sources of the issues that we found on the hill bench. Okay. And so just to summarize what we did model and code checks before functional testing to minimize rework. We then performed functional dynamic testing where we could analyze the model and the code for coverage and structural analysis. Showed just a brief thing about automation and how we can reuse the test assets to test the code as well. And then when we analyze the code from the integration, this is coming from 3 sources. We had stuff from hand code, right? And we had S-function code.
S-function, yep. And then that was it.
Yep, and then the model-based, yeah, the generated code. And then what we're really using here is we're using a lot of formal methods, right, to analyze, a lot of static analysis to go beyond and basically augment your functional testing. And again, this enabled more early testing of the model and code. And then ultimately, we had much more increased confidence in what we delivered to the customer.
That's correct.
So that's what we have today. So we're open for questions.